All right. So tonight we're going to go over a little bit of programming stuff. Um, I want to talk about how to set up Eclipse to do stuff. I want to talk a little bit about the basic structure of one of the simpler types of robot programs that you can write. And we'll look at a couple of different things on how you can set up a drivetrain to be controlled by motors that are connected via PWM to their motor controllers and stuff like that. The goal is to give you guys a basis of what you'll have to do. We'll do a little bit more on the hands-on day. Um, I'm still trying to decide how exactly I want to do the hands-on day. It really depends on how the drive base that is going to be set up or is going to be set up that day is configured. But I'm trying to play with some ideas in my head. It's been a little difficult because you guys' semester is coming to an end, and so is mine. So I've been up late doing homework, so I haven't had a whole lot of time to play with it any. Um, so the first thing I want to talk about a little bit is Eclipse. Um, Eclipse is the integrated development environment, or IDE, that you use for robot programming. Um, there are a lot of different ways to set up Eclipse, because Eclipse is designed to be extensible, so you can write in any programming language in Eclipse. But really all that we're concerned with is Java. So let me, I killed Chrome without realizing that I killed all of Chrome. If you go to eclipse.org, you'll be presented with this page. Generally speaking, the people that orchestrate the libraries and the plugins for Eclipse that are used for robot programming are really good at making sure that they stay working with newer versions of Eclipse. So just grab whatever the newest version is. It will be whatever you get when you click on download. There are different places to download Eclipse from, but most of them are no faster than the other. So you can just click download and a little pop-up will appear and it will start to download. Eclipse is a fairly large program, so if you're at the school, it'll be fairly fast to download. If you're at home or you're on a slower connection or something, it will take a while. But let's open up the Eclipse installer just to take a quick peek at it. Say that again? The installer itself is about 50 megabytes. Eclipse as a whole is about 300 without any of the extra stuff piled on top of it. It will come with the ability to do Java and stuff like that, but much beyond that. When you open the Eclipse installer, this is what you'll see. This was written by an organization called Oomph. Originally, Eclipse was just something that you unpacked and just dragged into a location and ran it from there. This makes it so that you can specify which versions and which pieces of Eclipse you want and download them. Normally, this window is based on the number of downloads of each version of Eclipse. Normally, Java is at the top because that's usually what Eclipse is used for, is Java. And you'll see other different pieces here. But the one that you're looking for is this one that's currently at the top right now, Eclipse IDE for Java developers. There are instructions on WPI's, Worcester Polytechnic Institute. They make the plugins for Eclipse. They do have instructions on their website that explain a different way of how to do this, that say you should install the C++ stuff first and then install the Java stuff on top of that. It's completely unnecessary, and I don't know why they teach people to do that. While some teams do program in C++, it provides no benefit to Java teams, and it takes twice as long to install everything and is actually a little bit more complicated to install everything. So if you select that portion, what you'll get is the installation folder where it's going to install, and whether or not you want to create a start menu entry and create a desktop shortcut. If those are all good for you, you can just click install. You can change the installation location. If you do, you may have a hard time finding it later, especially if you have to fix something. Normally, you don't have to actually go into the Eclipse installation folder and fix something, but every once in a great while, someone like me might have to if something broke or something got fiddled with that wasn't supposed to be. So usually using the default location is good. And if you have multiple instances of Eclipse installed, like I do, I have 2 different versions installed, it will be intelligent enough to not install over that other version. I'm not going to click install because, like I said, I've already got 2 versions of Eclipse installed. I can use one of them to demonstrate the rest of what I want to talk about. So let me open Eclipse. And I'm going to open Oxygen because Neon is the older version. And you'll be presented with a little splash screen, and then you'll be asked to select a directory as a workspace. Eclipse is based around the concept that you have separate workspaces for the different things that you're doing. I have a workspace for web development. I have a workspace for Python. I have a workspace for C++. I have a workspace for regular Java. I have a workspace for robot Java. And I'm certain I have others that I have forgotten the locations of. Yes, TJ?
Do you know the school's Wi-Fi password so I can download?
Sure. P. Only reason why I know it because they haven't changed it in 7 years.
Yeah.
Ready?
Yeah.
P. 0. W. 3. R. FU. 77.
What's so funny about that?
Not the intention, but hey. Yes, they changed the Wi-Fi password at the beginning of my sophomore year of high school, and it's been powerful since then. Why they haven't changed it now that everybody knows it, I don't know. Anyways, you'll be presented with a window asking you to select a directory as your workspace. Normally the default is somewhere in your documents folder. So like for me, that would be users, Brad L, documents, and then workspace. And that's where it's going to hang out. You can change this location. For our purposes, you really don't have to. I like to run all my workspaces in my Dropbox. That way, should something ever happen to one of my systems, I don't lose all my stuff. But that being said, in this instance, I'm just going to use the workspace that I already have set up. I don't know what's in this workspace. I don't think there is anything in this workspace, but we'll find out. And you'll see a splash screen again, and a little loading bar will appear, and it'll take a second. I've got a lot more stuff installed into Eclipse than you guys will have, so it does take mine a little bit of a second to catch up. But when you open Eclipse, you'll see this window. This is just the welcome screen. It won't always pop up for everyone. I find that unchecking this checkbox is very inconsistent as to whether or not it actually makes this screen pop up or not. I usually end up having to go click on the workbench button regardless of whether or not I've unchecked that box. But this is really what you want. When you click on the workbench button, you'll be presented with whatever projects are in that workbench. In this case, I apparently do have a project in here, and I think I remember what I was doing to try to test something. There is a lot of extraneous stuff that opens up when you open the Java workbench view. I tend to not particularly enjoy how cluttered it can be, so I close things like the task list, the outline, the problems view, the Java doc view, and the declaration view. They're not helpful to me. unless I'm really looking for something very, very specific. Sometimes I'll reopen the outline. And anything that you close in Eclipse, you can actually click on Window and then Show View, and most of them are right here for you to grab, like the outline. But if it's not, you can just click on Other, and there's a whole list of things in different folders that you can pull up if need be. But this is generally, if you're working with me, or if you're working with somebody who I've helped teach, this is probably what you're going to see. You're going to see the Package Explorer on the left and the actual code on the right. And I tend to keep it this way just because it's a little bit cleaner, and it gives me more real estate to actually see what code I've written as I'm going down. When you first install Eclipse, the stuff that you need for robot programming isn't all there. There is a couple of things other than what I've shown you already that you have to do. Eclipse, like I said, is extensible, and it uses something called a plugin system. I don't know how many of you are familiar with Minecraft. I'm assuming all of you. It's very similar to Minecraft modding. Basically, what you want to do is you want to click on Help, and then click Install New Software. And this will bring up a separate window, and it will have a Work With field with a drop-down, an Add and a Manage button, and then an empty checkbox list. The first thing that you're going to want to do is you're going to want to add the web location that has the plugins. I already have it set up. I'm going to click on Manage just so you guys can see what it looks like. So this is essentially the same thing that you're going to see when you click on Add, which is what you're going to want to do to add this. I always call it FRC plugins. You can give it whatever you want for a name, just so long as you don't give it something completely arbitrary. That way, if somebody goes to fix something in your Eclipse installation and they see banana, apple core, orange in the list, that's not going to tell them anything. What's really important is the location. This location is actually on you guys' website under Resources 2016 Software Updates. I tend to periodically go back in to your website because I used to be this team's webmaster and fix the links on those pages so that the downloads actually work, just because they can be exceptionally hard to find. But this one that is fairly consistent, and generally speaking, I'm not going to read it out to you because you won't catch it all, but you can just go to the website and copy and paste it into the location field and then click OK and you'll be all set. So once you've done that, once you've added the site, you'll want to change the drop down to say FRC plugins. And you'll see WPI robot development. And if you open the drop down, normally you would see two things. Now, like I said, I've already got the stuff installed, so let's not go there. But if you open the drop down for the checkboxes, you'll see Robot C++ development and you'll see Robot Java development. The one you want to click on is Robot Java development, obviously. In this case, I'm going to show you the steps of how to work through the rest of the windows using the Robot C++ development. So if I click on Next, it's going to say Calculating Requirements and Dependencies, and it's going to sit there for probably 10 to 15 seconds. Mine was a little bit quicker because I'm gauging this off my home internet connection. And it will give you an install details list. You don't have to worry about that. Just click Next. You'll have to accept a license agreement. You're welcome to read it if you want to spend the time. I don't. And then just click Finish. And you'll see down in the lower right hand corner, it will say Installing Software. And if you're on a Windows 10 system, the progress bar will actually show up on the Eclipse itself, the Eclipse icon itself on your start bar. When it's finished grabbing everything that it needs, you're going to get a security warning. The plugins for FRC robot development are not signed. Just click Install anyways. It doesn't matter. You're not going to get a virus. I promise. If you click install anyways, the window will disappear and you'll see the progress bar down below continue along, and after it's done, you'll see you need to restart Eclipse for the changes to take effect. If you're working on something, you can click no and keep working, but your new plugins aren't going to work until you push restart or close and reopen Eclipse. I'm going to click restart now, just get out of the way, just so that it doesn't bug me later. And it will show you the splash screen again. It will ask what workspace you want to use again, and then you'll see the progress bar appear. Or maybe it's not going to ask me what workspace I want to use. Maybe my computer's just going to eat it. Nope, okay. So we'll go back to the workbench. So that's the very general setup of Eclipse. That was very, very fast. I do have another video on YouTube that's under the Lawrence Programming Videos playlist that I can provide, that has just one 20-minute video that goes through everything about installing Eclipse in a little bit more of a concise and less rushy way. But that being said, I want to talk a little bit about the structure of a robot program. I'm going to remove a little bit of junk from this example that I'm not going to be using, just because it's unneeded clutter. And I'm going to use it to talk about, I don't know what's going on. All I know is that my trackpad is right-clicking when I'm not right-clicking. There we go. I removed the comments, which we'll talk about that in a minute, because they're not actually helpful. I don't know why they don't actually make them helpful. But, so, if you're writing a robot program that is a single file program, it only has one file that is a part of it, this is what you're going to see when you start off writing your program. And in fact, there is one other thing that I'm going to add to this real quick while I'm talking. I want to show you guys the different parts of how your robot code runs. So the top part right here is something called your import statements. Java and the libraries that make up the robot programming portion of these plugins that we've installed, there are a lot of different files that do different things to accomplish tasks in Java. And because of this, when they made Java, they created something called the package system, which is basically just organizing the different files into folders. And when you want to use something, you call import, and then you put in the folder path separated by periods. Now, over time, you will get familiar with the different paths that you need to import in order to do things. And we'll see in a minute how Eclipse can help you deal with finding out what is where. It doesn't leave you completely in the dark, but you do have to have some semblance of an idea of where you need to go if you've not typed something correctly, or you may not know the actual name of what you want to use. But that being said, we'll have more import statements once we start adding stuff to this program. The next piece is public class robot extends iterative robot, and you can see that there are brackets surrounding stuff that is indented under that text. Java uses brackets and indentation to help you sort of visualize the structure of your program. You'll notice that Eclipse will try to help you with this indentation, and it's usually pretty good at it, but it will have a hard time if you forget brackets. The brackets help to define the scope of whatever it is you're writing. Basically, what I mean by that is you encapsulate different pieces of your program in different sections. Hopefully that makes sense. In this case, we encapsulate everything that makes our robot run at different periods of a match inside these brackets. And there are 6 different pieces that I want to talk about. The first one is robot init. Robot init just stands for robot initialization. It runs when your robot first boots up. Robot init is where you do all of your general setup. You connect to your motor controllers. If you've got any sensors, you can make sure that they're working and that they're reset to 0, stuff like that. You want to make sure that everything that you need later on in the program is available to you at that point. The next one is autonomous init, which just stands for autonomous initialization. It is run just before the autonomous period starts, where your robot does things on its own. Autonomous init is more for doing that same reset procedure, making sure that, if you've got multiple autonomous modes, you check the switches or you check your dashboard on your laptop to see which mode you're running, things like that. The counterpart to that is autonomous periodic, which is where most of the meat of your autonomous program is going to run from. Autonomous periodic runs for that full 15 seconds during a match. I don't know, how many of you are familiar with the structure of a match? TJ's shaking his head. Everybody else is not.
Define match.
So, like, you go up onto the field to play a match. Okay?
You mean like how it's actually set up?
Like Hunter, you have some experience with this. You bring the driver station up onto the field, you plug in, the robot gets put on the field, and you run a match. Does that make more sense?
Yeah.
Okay. So, TJ's shaking his head. I can't read anything from the 3 people in the back. So, what are you guys familiar with? And I want to make sure that I fill you guys in the best that I can, and all 3 of you are quite quiet, and I just want to make sure I'm not missing anything on you here.
Well, I understand the part about putting the drive station up and that start the robot up, but I don't know, like, when the...
Are you having fun over there, Pete?
Getting ready to be user friendly with my phone.
Also, I'm having some issues. I'm using Linux and it's not really working.
Linux is different. You and I will have to talk.
Do I have to download it on Windows or?
No.
Okay.
It's just a little bit different.
So I don't know, like, when the autonomous stuff comes in.
So let's talk a little bit then, because I want to make sure that you've got it down. So there is a server box. If you talk to any of the people that run the field, they'll call it the Scorpion box. There's a server box that runs the field, and there are 2 boxes at either end of the field that help to facilitate the communication with the main box. What happens when a match starts, or what happens when you push enable on your driver station here at home when you're connected to your robot through Wi-Fi, is either one starts to send something called control packets to the robot. The robot can then send information back and do different things, but the primary communication is control packets from your driver station, either directly to the robot or to the field. And depending on what the field says, warps those control packets a little bit. So at the beginning of the match, the first thing that happens is the control packets are modified to tell the robot, run autonomous init. If you're running a full match, it will tell your robot, do this. You've got such and such amount of time. The next thing that happens when the robot returns that it's done, the field says, okay, start running autonomous periodic. And the field will, every 20 milliseconds, shout at your robot, autonomous periodic, autonomous periodic, autonomous periodic, over and over and over again, until the autonomous period is done, which is 15 seconds. That's the part of the match where your robot is doing things that you programmed it to do on its own to score points. You don't have any control. Immediately after the autonomous period ends, there is a very slight break. It's about another 20 milliseconds long. It's because the field is doing stuff. It actually disables your robot for a second and then re-enables it. It then shouts at your robot, run teleop in it, which is the next thing that I was going to talk about. Teleop is the part where you're actually controlling your robot. It's usually 2 minutes and 15 seconds long during a match. Once that is done, the field starts shouting again. Teleop periodic, teleop periodic, teleop periodic. And marching bands your robot into doing whatever is in your teleop periodic method over and over and over and over and over again. And that's the general structure of a match. It's basically either the field or whatever computer you're using to control your robot shouting what it wants your robot to do, and your robot just runs the code that it's being told to. There are other things that come through in the control packets, like joystick and Xbox controller information. The things that you're doing on the Xbox controller are actually sent to those same control packets. And there are other packets that get sent back and forth between the robot and your driver's station for things like logging. If you're using cameras on your robot, those are separate packets that come through on separate connections. Some teams use separate computers on their robot. There are a lot of teams that use Raspberry Pis. I don't know if you guys have ever seen a Raspberry Pi. Another popular one for vision processing is the NVIDIA TK1. But the general idea is the field management software is the orchestrator and just repeatedly beating your robot into doing what it's supposed to be doing.
With the Xbox controller, do you have to have your own separate function for that, or can it be included into the function itself of teleop?
I think I know what you're asking. Wait until I get to controllers. Okay? Because I think I know what you're asking. I think. I'm not quite sure. But does that clear that up a little bit more? Anything else that you guys think you want me to cover a touch before I continue? No?
Actually, one thing, at the end of the match, does it automatically cut off all the code when, like, that final buzzer goes off?
So when the buzzer goes off, there is a slightly different step. There are actually different pieces that I've not added to this window that, for the most part, teams don't use. I do have some examples that I've written that do use them. They are disabled init and disabled periodic. The field is constantly telling your robot to do something, and so is your computer. If the robot is not in communication, you'll actually get errors. And then the robot will go into a fail-safe mode where it stops motor control. It prevents certain things from running, like solenoids, which control airflow for pneumatic systems and stuff like that. So disabled init and disabled periodic filled that space. Basically, when your robot is not running a match, the first thing that it does when it's told not to run a match is it runs disabled init. And then, again, every 20 milliseconds, disabled periodic, over and over and over and over and over again, until your robot's told to do something else. And like I said, most teams don't make use of it, but the thing about the disabled methods, the things that I described that are similar to these, disabled init and disabled periodic, is they don't allow things like motor function, solenoid function. If you tried to use your robot during that time, your robot's literally not sending control information. It's just sitting there. And if you tried to actually forcibly move a motor in one of those sections, it wouldn't work. You'd get a whole bunch of errors in your console that say, essentially, tried to move a motor when you weren't supposed to. So no. Once your robot is told to stop by the field, 99.9% of the time it is going to stop. There have been situations where robots don't, and they are a bit scary, but most of the time they stop. There are provisions on the field that if a robot does not stop, there are ways of forcing it to stop. Sledgehammer, no. Sledgehammer, no. But there are your driver's station. If you push the space bar, will emergency stop if your robot's enabled, and you'll have to reboot your robot in order to use it again. Each driver's station on the field has an emergency stop. The head referee has a global emergency stop, so if the head referee on the field needs to stop all the robots all at once, they can. And the scorekeeper, working with the FTA, can also perform either controlled or a global stop on all robots with an instruction from an FTA, a field technical advisor, or an FTAA, a field technical advisor's assistant. I used to be a scorekeeper for Pine Tree, the competition that happens in Lewiston, and I have had to perform stops before because a robot got out of control. It ripped somebody's bumper off. It ripped something else off another robot, and the team wasn't stopping when they were instructed to, so I stopped them. But that being said, the general structure of a robot program is when your robot first turns on, robot init gets run. When your robot is told to run a match, autonomous init gets run first, and then it repeatedly calls autonomous periodic roughly every 20 milliseconds. Once autonomous is over, it calls teleop init almost immediately, and then after that, it's teleop periodic until the match ends, in which then the disabled parts of it take over. So, any questions about that before I continue? No? We're good? Okay. So the next thing that I want to talk about a little bit is how you could put together a simple drivetrain program. When I tend to do this, I tend to stick with what teams normally do when they first start out. Last year on you guys' old robot from last year, you guys used a different communication style than what most new teams do. Obviously, 2648 is not a new team. That's probably the only one you're familiar with, if you're familiar with them at all. But in this instance, we're going to set up motor controllers if we were going to use PWM or pulse width modulation to control the motors. Now, I know TJ, Connor, Hunter, Isaac was at the last thing that I did. I think you two were, but I don't think I caught your names.
I don't think I opened. Mine's Owen.
Owen?
Caleb.
Okay. Owen and Caleb. It's going to take me a little while. I hope you know that. Don't laugh at me, Pete. So I don't know what you guys have seen. You've probably seen, if anything at all, a whole bunch of little tiny black rectangles that are all bound together, and there are these two, one yellow, one green wires that are all daisy chained together and then connected back to the Robo Rio in some way. Those motor controllers are called Talon SRXs. They're probably the most commonly used. The next runner-up right now being the Victor SP. And those are currently set up to use something called CAN. Now last time when I talked about CAN, we talked about how it was the shouty communication protocol. Oh my goodness gracious, great ball freaking fire. Get out, Colby. All right, give me a minute. I hate my friend Colby.
Player like boss. Yep.
I had forgotten I'd left Discord open. That was dumb. Here we go.
3 seconds later.
All right. Those are connected using CAN. And CAN is the shouty protocol. Everybody has a number. When you want to talk to somebody, you shout their number. They hold their number up, and then you can start talking back and forth.
They should do that in classrooms. Yeah.
They do kind of do something like that in classrooms. It's called raising your hand.
Never heard of it. I don't do that.
CAN is really powerful because you only have to use 2 wires, plus whatever you need to use to power it. PWM is a little bit less complicated usually to set up, but you have a signal wire, and a ground connection for each motor controller that you want to use. So it tends to make a mess. What is more commonly referred to as a rat's nest. That being said, there are some caveats to CAN and there are some caveats to PWM. It really depends on the team and what they want to accomplish with their robot. Usually, if teams want their wiring to look really nice and pristine, they're going to use something like CAN. But I have seen configurations with PWM that do look just as nice. But in this case, just to start off with, I'm going to show you how to make a drivetrain movable using just PWM. So the first thing that I'm going to do is I'm going to define the names for my motor controllers. So private, Talon, SRX. No, I don't need to do that. Not anymore. Left side, private, Talon, right side. So that was fast.
Sorry, one thing I was actually gonna ask earlier, but I forgot. What is the override?
Oh,
I've always wondered that too.
that's a little bit more of a complicated topic, but to give a very quick rendition, if you look at the near top of the program on line 6 where it says public class robot extends iterative robot, that part extends iterative robot is what is causing that override thing to appear. Basically, these different blocks of code are commonly referred to as methods. Different repeatable functions of things that you want to be able to do over and over and over again. When you override a method, it usually means that the method has been defined somewhere else and you want it to behave differently in your version of whatever it is you're writing.
Then why can't you just name it something else?
What?
Why can't you just name it something else then, if it's already overriding? Like, if it's already defined somewhere else, a function, then why can't you name it autonomous periodic 1 or 2?
Because, and this gets into a concept called polymorphism, which is very, very difficult to explain to new programmers. TJ, what's your last name? Petrillo? Okay. So, you have a last name that defines a lineage. This is sort of the same concept. You can think of the word or the set of words iterative robot as this file's last name. It defines common characteristics and behaviors for that particular something or other.
So you're saying it's a type of function. It's not a function on its own. It's like a whole class of functions.
Sort of. Because there are things in iterative robot that do things. The overrides here, they don't actually do anything. If you left these out, when your robot got to that part of the match, it just wouldn't do anything. It'd just sit there. The method would still get called over and over again because it does exist somewhere else, but it's empty. It just doesn't do anything. You can think of it sort of like this. My last name is Bickford. My dad has two different colors of eyes, and my eyes are two different colors, usually. Um, he actually has a condition where his eyes change color, and so do mine. My mother has really blonde, curly hair. If you've ever seen a picture of me with long hair, you'll know that if I let it grow out, it gets the same way. Those are characteristics that I share with my parent. Just like Robot shares characteristics from Iterative Robot.
So it's a child.
It's a parent-child relationship.
Well,
That's literally how it's defined.
Like, I remember, like, there's things called parents and there's things called child. I don't know if it's Java, but I've used JavaScript or C
Right.
Sharp. But basically, the parent controls all of the childs, which...
Essentially. So in this case, the parent is Iterative Robot, and it has robot in it, autonomous periodic, etc., etc. We can redefine those because we are a child of that class to do other things, behave in the way that we want to. Just like you don't act exactly like your parent or parents, neither does this have to. You can redefine how you want it to act. I am not exactly like my dad. I don't want to be a cop. Freaks me out. Don't want to work for DHHS. Just seems boring. So I work on computers. I build ridiculous projects with LEDs. I do different things. My dad is very mechanically minded. I am not. I can put gearboxes together with instructions, but I'm going to defer to someone like Pete if I need to do anything more complicated than that. But that being said, yes, the reason why override is there is it is a parent-child relationship. And what you're doing inside Robot, what you're doing in what we're doing right now, is actually redefining some of the behaviors of Iterative Robot. And we do this because the way Java works is when it calls on those methods in Robot to do particular actions, Java is actually looking for something that has a parent of Iterative Robot. Okay? Is that it seems to make sense to TJ. It was a big mess of information that I didn't expect to go over.
I think we can start more basic. So as far as like some of the code that we've seen before, before you started naming them, you had to actually initiate them. Like there's a class somewhere called Talon that defines what Talon can do.
Yes.
And you've got to make sure that that's lined up before you start doing much with that.
Right. So in this case, let me define just a couple more things. And we'll just stick with this for now.
I think that was a question that we had when we went to the Sears port. It was like, well, how do you know the secret name of all the codes?
Right.
So it's sort of like there's this magic laundry list of 50 different things that you need to know so that you can say, hey, go get this piece of code so that you can call it something and tell it to do something else.
And there is a magic laundry list, and I'll show you the magic laundry list before we get on tonight. So what I've just done is I've created the names of the 4 pieces that we need to actually make this work. They're not filled out. They don't have the information that they need to work. That's a process called initialization. We'll talk about that in just a second. But basically the general structure is what you do is you put the definitions in under that header piece, public class robot extends iterative robot. In this case, I put 2 talons, one for the left side of our drivetrain and one for the right. I've created something called robot drive and called it DT. And I've created something called J1, which is going to be a joystick. These are different ways to represent different objects in Java. Java in of itself is an object-oriented language, meaning that when you create stuff to work with, it's usually based on, or at least loosely based on, a real-world object. So when you are writing robot code, a lot of what you'll see is the names of the things that you actually want to make use of in the code itself. There are some exceptions, because there are some things like switches which are pretty generic. Is it on or is it off? So, but not everything is a switch. Something might be a switch, it might be a button, etc., etc., etc. But we'll get into that. So, one thing that you guys probably noticed is the red underlines under everything. Specifically, the names of the things that I've created. I don't know how well this shows up over here. This means that the file that you're currently working in can't find the names that you're asking for, the types, as it were. But like I said, Eclipse will help us. So next to where there's a problem, you'll see a little light bulb with a red X. And if you hover over it, it will tell you what the problem is. In this case, it says Talon cannot be resolved as a type. That just means that it doesn't know what Talon is. It doesn't have any information about how it needs to work or what it does. If you actually tap on it, if my computer would cooperate, it will give you a list of options. Normally the first one is what you want, and in this case it is. It says import Talon, and Eclipse has actually gone out and looked at all the libraries that you have installed and said, oh, this is defined here. I'll just grab it. And if you click on that, you'll see that our list of imports at the top changed, and it will highlight it in gray, and it will show you the path of what it is that you just imported. And we have to do that for robot drive and joystick as well. And you'll see them get added to the top one by one. And normally, Eclipse will make an effort to organize your imports in alphabetical order. Doesn't always work, but usually does a pretty good job with smaller programs. So, like I said, these four things aren't filled out at all yet. We've created names for them, but they don't have the information that they need in order to work. So what we're going to do is we're going to start defining things. Now, remember how I said that robot init happens when your robot first boots up? This is normally where you would want to do that initialization step, that filling in of information for the names that you've created. The way we do that is we say the name that we want to fill in. In this case, I'm going to start with the left side of the drivetrain, the motor controller for the left side of the drivetrain. And I'm going to say equals new Talon. And then I'm just going to put a 0 in here. And then a semicolon at the end. So what I just did was I said left side, that name, is now equal to a new instance, a new version of a Talon. Some physical object that I want to make use of, and I'm going to provide it with a value of 0. Now, the value of 0 may seem arbitrary, but it's really not. On the RoboRio, if you're looking at it with the USB ports on the top, it should be the left side. Yes, the left side. You'll see a whole bunch of pins, 3 across, all the way down. And it will say PWM, and then it will show you a pinout on the bottom of the different pieces. And then numbers next to each set of 3 pins. 0 is the first set of pins closest to the top. That's where the signal is going to come out of in order to control your motor controller. You can use all of those ports, and in fact, there are more on the robot than just the 10 that are there, but most teams don't go beyond that. So we're going to do the same thing for right side. Now, would it make sense for me to put 0 here?
No.
Okay, good. I'm glad that everybody got that. Because you wouldn't want both sides of the drivetrain behaving in the same way, especially if you wanted to turn. So what we'll do is we'll create those two, and that will give us the ability to interface with the motors on our drivetrain. Now, actually getting motors to move as a drivetrain is a little bit complicated, at least depending on the version of control that you want to use. Tank drive's pretty easy, arcade drive is harder, and Mecanum drive I wouldn't want to write on my own. So, robot drive is what we actually use for that. It is an inbuilt system that was written for robot control that allows you to put motor controllers in it and then use that in order to control your robot with. So what I'm going to do is I'm going to say dt equals new robot drive, and then I'm going to say left, whoops, that's not what I wanted to do, left side, right side. So basically, what I've done is I've created a new robot drive that I'm going to store in the variable named dt that has the left side of the drivetrain and the right side of the drivetrain. Now, what do you guys think would happen if I flipped left side and right side?
They would basically be reversed. Or the wrong way, or go backwards.
Right, so sort of. There's a specific definition for robot drive. It wants a particular order of motor controllers. It wants left first in this scenario and right second. So I can't exactly picture in my head what it would do, but I believe it would just be inverted control. But
We do that on the road. The first one we did last time, we had that problem.
oh yeah, because Justin put them in backwards.
Turn right, and it went left, and everywhere else.
That's about right.
That was one of the days that I wasn't there.
Yep.
Yeah.
The good old days.
Good old days. Oh goodness.
Brad,
Yes.
Lisa wants you to take a break at 7. Just 10 minutes or so.
Oh, okay.
Okay?
Yeah, we can do that.
And TJ, she wants you to call your mom to make sure that she comes and gets you at 8 o'clock.
Yeah, well, actually, my mom is in my sister's.
You're at the concert. Okay, because she did say if you mentioned concert, then that was fine.
I basically am staying here to my sister's concert.
Okay.
Right. Yeah, but anyways, those are the 2 messages that she texted me.
Okay.
It's gonna come over, like, it's gonna be over at the same exact time as this.
Right, about the same time. Right. Yep.
Let's do one last thing before we put our brakes on for a quick break here. Let's create our joystick. Same sort of deal. J1 equals new joystick. And then I'm going to put a number in here that we've already used. And I'm wondering if anybody can quickly tell me why.
Because action mappings.
Because what?
Action mappings of the controller. Each controller has different numbers of buttons.
Not action mappings.
So you can get the controller to actually control whatever's going in that order.
Close. So when you create a joystick object, which is what we just did, that new joystick 0 thing, when you put a number in there, you're actually defining what port on your driver station that joystick is connected to. This makes it so that you can have up to, I believe, the limit now is 6 controllers. There's no reason for you to have 6. Most teams have 2. But that is just, you can think of it as the USB port. You can reorder them in the driver station, so it's not based on USB port specifically. But it is essentially bound to a particular controller on the driver station. But that being said, 7 o'clock is here, so let's take a quick break, and we'll come back to deal with the last part, which will take all of 2 seconds. All right, so we only have one piece left in order to actually make the robot move. So what I'm going to do is I'm going to come down to teleop periodic, and I'm going to say dt and then put a period. And basically what that does is it shows me all of the different abilities of robot drive, specifically the robot drive that I created that's called DT. And you'll see a whole list of things. It's going to give you the suggestions that it thinks are correct. And actually the one on the top is the one that we're going to use. In this case, I'm going to make the robot move like it's an arcade drive. So you've all used like an arcade machine, right? Where it's got the joystick in the middle and it goes like this, correct? I'm not that old yet.
Are you talking about like the ones that a lot of teams use with that little junky controller?
Like an aircraft controller sort of deal. And you could also think of it in the same way as like the left stick on your Xbox controller or something. Same sort of deal. In this case, what I'm going to do is I'm going to select arcade drive by pushing enter, and it's going to ask me for something called a generic HID stick. What does that mean? Basically, it's asking you for something to control the robot with. In this case, I'm just going to provide it with J1, because J1 is a child of generic HID, so I can pass it in. And that's it. If you ran this robot code onto your robot and enabled your robot and started moving a joystick back and forth, it would move. It may not move, depending on how your motors are hooked up, it may not move forward and back, left and right correctly, but it will move. Hunter.
I worked a little bit with the C+, because that's what I'm doing for Vex.
Mhm.
Can you set your motors to go at a certain speed so when you do move the joystick, it can do that? Because
Like a speed limit,
yes,
or
a speed. Well, basically, I guess what I'm asking is, when you move it forward, you have to go a certain speed.
Well, I'm guessing like you could probably put it as a float, like have it from 0 to 1, so you can have like a kind of like a percentage of speed.
so this does ranging speed automatically based on the joystick. If you move the joystick halfway forward, your robot will move forward at half speed. If you want to directly control the drivetrain itself, there is a mechanism for doing that. So let's say in the autonomous period, we just want the robot to drive forward at 33% speed, let's say. The way we do that is we say dt dot and then set left right motor outputs. And it's going to ask you for a left output and a right output. If you want it to move forward at 33%, you just type 0.33 and 0.33. And it will move forward at 33% power until autonomous ends. Because, like I said, autonomous periodic gets called over and over and over and over again. So basically, what's happening here is there is something that runs on the RoboRio called the watchdog timer. It used to be a big headache. A lot of teams used to disable it, which is bad, but first didn't really care at the time. But now it works. The watchdog timer, basically what it does is it verifies that your robot is receiving control packets within the 20 millisecond time frame within a certain level of error. And if it's not, it shuts down your motors. What happens is every time either autonomous periodic or teleop periodic is called, each method that manipulates a motor has that watchdog check. And if at some point or another in the chain, the watchdog doesn't recognize something correctly, it will cut your motors off until it starts receiving the information that it's expecting. This is the same sort of deal. So you're moving forward at 33% power and autonomous, and all of a sudden your radio cuts out. Immediately, in the next 20 millisecond cycle, your robot says, stop all motors. There's actually a piece of hardware on the robot, the FPGA, that actually manages PWM. And basically the RoboRio tells the FPGA, stop all PWM function. Don't do anything. Just stop. And the FPGA is just like, okay, and it sits there. And when the RoboRio sees that it's getting information again, when that watchdog timer is no longer looking for information, then it will say, okay, FPGA, you can keep doing what you're doing. Does that make sense? Are we good with that? Okay. So let's talk. This is the part that's hard because some of this stuff would be nice to be able to demonstrate, which I hope to be able to do on the, at least in part, on the hands-on day. But I would like to talk about it a little bit beforehand. I want to show you guys how to make a bumper switch. So if your robot hits a wall, it stops. If you did Lego robotics, probably pretty familiar with it. You hit a wall, you want to stop. You hit an object, you want to stop. So to do that, we use something called digital input. On the opposite side of the RoboRio, if the USB ports are on the top, on the opposite side from the PWM ports, there's a whole other big rail that's called DIO. It stands for digital input and output. We talked about it the last time. This is where all of your switches get plugged in, and if you wanted to run like a couple little LEDs or something, you could put them there as well. There are other things that can plug into it that make use of it. Digital sensors like encoders and ultrasonic sensors make use of digital I/O. We won't go over that tonight, although I might bring an ultrasonic sensor with me if I can find one on the hands-on day. But for this instance, I'm going to show you guys how to make a digital input. You can imagine it just as a push button. It's going to be facing out from the front of the robot, and when the robot bumps the wall, we just want it to stop. So I'm going to define something new here, give it a name, and make sure I have the proper import for it. And then I'm going to define it. And as you'll see, I was programming in a different programming language today, and you have to capitalize the N in new in the language that I was writing in to make it work, and it's blending all together. You'll notice that I use 0 over again. The numbering system for DIO starts over again, so you'll see listed next to each set of 3 pins, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Same sort of deal. Whatever you plug it into or whatever you plan on plugging it into, that's what that number needs to be. And what I'm going to do is I'm actually going to demonstrate this in autonomous periodic, because normally, you know, if you're driving in teleop and you smash your robot into the wall, you're going to have enough sense to not keep driving forward. At least I would hope that you would. So... So it doesn't really make much sense to have the bumper button killing your motors, especially if the bumper button hits another robot and you're trying to push them out of the way and all of a sudden your motors stop dead. That doesn't really help you any. So we're going to show you in autonomous periodic, because one of the things that is problematic for teams is when they're in autonomous, if their robot goes rocketing forward at however many feet a second, 14 to 20, and hits a wall going full speed, you might break something. So it's good to have a stop there. So what I'm going to show you guys is something called an if statement. An if statement takes a true or false, commonly referred to as a Boolean value, that basically is used to answer a yes or no question. You can have multiple levels to an if statement. In this case, we're only going to have two. But you can extend it down as far as you want it to go, depending on the number of conditions, the number of true-false scenarios, the number of questions that you want to ask. So I'm actually going to remove this piece for a second. And I'm going to say if bumper.get, and then just for sake of sanity here, I'm actually going to type out equals true. And then down here, I'm going to put else. So when our button is pressed, it's going to return true. So when I say bumper.get, I am telling the roboreel to check connection, DIO connection 0 on the robot, and see if the electrical signal coming into it indicates true. If it is true, I want to stop. So what I'm going to do is I'm going to say dt.stop motor. And that's it. That will make sure that the motors on the drivetrain stop. And then I'm simply going to replace what I had before into the lower portion. And what will happen is, so long as that button is not pressed, the stuff in the lower portion will happen. And when the button is pressed, the stuff in the upper portion will happen.
With the DT stop motor, do you have to clarify which motors you want to stop? Or
Nope, it's going to stop them all. If you want to stop a specific motor, then you should be writing something other than robot drive to facilitate your drivetrain. Because robot drive is going to override whatever changes you make to left side and right side. Like, Talons have a method called set, where you can set the output just like you would set left-right motor outputs. You can set it to a -1 to 1 value depending on what direction you want the motor to go and how fast you want it to go. But if you do that, the next time robot drive updates, it's just going to override that change. You might have some funniness with how quickly your robot moves if you have a whole bunch of different values in there, but it's certainly not going to stop your motors like you would expect them to. The stop motor method, that action, is there to be an easier way of writing dt.setLeftRightMotorOutput 00. I mean, I could literally write this and it means exactly the same thing as what I had there before. It's just you lose the fine-grained control of your motor controllers themselves when you hand them over to robot drive. There are ways that you can play with it that you could make it work that way. I have never seen a team give me a reason, let alone give me a good reason, why they would want to. That being said, I'm certain someone could find a reason. But that's the basic idea of an if statement, is you're putting in some true-false value to do one thing or the other. What else do I want to talk about? Does anybody have anything that they want to know? I'm going to go with... TJ's been asking questions all night long, and I'm trying to... Caleb.
Yeah. This little thing you just wrote here, I just got thinking about this. If you have this button on the front and you hit the wall,
Mhm.
and then it kills all the motors. you wouldn't have backed up from the wall at all, so the button would constantly be returning the value of true, so the robot would just stop.
So I may have made this sound like it was more permanent than it actually is. Remember that the field management system and or your computer is in control of your robot at all times. So when autonomous periodic ends and your robot switches to teleop, whatever happened in autonomous periodic or was happening in autonomous periodic doesn't matter anymore, because you're calling a completely different part of your program. When you're in autonomous and you've gone by autonomous init, this is what your robot is concerned with: autonomous periodic and the stuff inside it. When your robot's in teleop and it's done teleop init, the stuff inside teleop periodic is what your robot is concerned with. What happened before, as long as it's not still happening now,
Yeah.
it doesn't really care.
Okay. Yeah, I read over the autonomous part, but so pretty much, if that say that happened in the first couple seconds of autonomous, would it just be disabled for the rest of the time?
It would just sit there for the rest of autonomous, yes. Normally an autonomous like this wouldn't necessarily be so basic. Some teams, for certain games, can actually write autonomous programs that are like this, that are actually useful to the game. As of the past couple of years, that's not been the case. A lot of the autonomous periods in the past couple of years have been relatively complicated. So having a bumper mechanism is not necessarily always going to be something that you'll make use of. But this is just an example to demonstrate if statements. There was a couple of years ago, was it two competitions ago, with Stronghold?
Yep.
The one that looked like castles. Part of autonomous was if you could breach a defense, which was something,
Go over a ramp with
go over a ramp or something, go over a moat, go under a drawbridge, something like that. If your robot could do that during the autonomous period by itself, you got X number of points. It was either 5 or 15. I know it ended in a 5. Normally for something like that, you would use some sort of indicator. Normally you wouldn't use a bumper. A lot of teams used timers. And in fact, I'm about to show you how a timer works here in just a second, because that's one of the more common ways to do a peaky autonomous without sensors. And it's a really easy way to hash out an autonomous without actually having to incorporate a whole bunch of sensor code into it. Yes, Hunter.
I noticed in the last competition, since that was technically my first year, a lot of teams, well, not a lot of teams, but some of the teams had the choice of doing multiple autonomous codes. Do all they have to do is just rewrite different codes and then set it to, like, if button 1 is pressed, do this code and stuff like that? Or?
Yes, actually, that is the essential gist of it. Some teams do it a little bit differently. Some teams actually have physical switches on their robot that it is the responsibility of the people that put the robot on the field to change based on wherever they position the robot on the field. And in other cases, teams will use something called the Smart Dashboard, which is a Java-based application that actually runs in your driver station that you can push controls to, like buttons, radio buttons, text fields, and stuff like that, to both get information from your robot and send information to your robot. Most teams, what they will do is in autonomous periodic, they'll just put several if statements that look up those values, whether they be physical or in software, and make a determination as to which version of their autonomous code they're going to run. Some teams will break them out a little bit differently, and there are other ways to program a robot other than this. This is the most basic form that WPI recommends that you use. I'm not going to go into what is commonly referred to as command-based programming, because it requires a more heavy-handed knowledge into how Java works, which I do not have the time to cover in 2 hours. It goes back to that parent-child relationship and having multiple files that are based on each other and make use of each other, and it ends up getting very complicated quickly for a new programmer. That being said, it would be good for you guys to know it, and I'm more than willing to teach, but with it being so close to build season, it's hard to cram something like that along with Java into a space of time, like what we have left. So that being said, let's talk a little bit about a timer, just really quickly here. So as I said in the electrical portion of what we're doing now, the FPGA is what keeps track of time on the robot. And there are ways that you can actually look up those times and make use of them for different parts of your program. So what I'm going to do is I'm actually going to leave this piece of code right here, and I'm just going to comment it out. Now, normally a comment would be used to actually add some sort of meaningful information to your program, like how something works. In this case, I'm just going to comment it out so that that part of code doesn't run. Anything that isn't a comment won't actually run on your robot. The easiest way to make a comment is put 2 forward slashes and then start typing. That only works for a single line, though. You'll have to put forward slashes on every line that you want to make a comment. If you want to make a proper block comment, you put a forward slash and then a star, and then Eclipse will autofill the rest when you push enter. But that being said, let's try to construct a timer-based autonomous. So I think what I'm going to have it do is drive forward for 2 seconds, and then pivot right for 1 second, pivot left for another second, and then stop. So private timer. That's all we got to do for that. And what we'll do is we will add the import. Now, there's a lot of different timers in Java. If you're doing robot programming, the first one that should show up is the one from WPI. You can clearly figure out which one is from WPI because it will have WPI twice in the name. And then what we'll do is down here, we'll say timer equals new timer. So right now our timer is not really doing anything, it's just sort of sitting there idling. What we want to do is inside autonomous init, we're going to say timer.reset. I just do that out of habit. You don't necessarily have to in this instance, but if I was using a timer somewhere in like teleop periodic to do something repeatedly every few seconds, I would want to remember to call reset. And then you're going to say timer.start. Now, remember that autonomous init happens just before autonomous periodic starts going over and over and over and over and over again. So you can do this, but just make sure that you call start last in autonomous init for whatever you're doing. Otherwise, there may be a time delay that uses up some of your autonomous time that you don't want it to. Because the init methods have a little bit of leeway with how long that they can run, as opposed to the periodic methods where you have about 20 milliseconds plus or minus 5, and that's it. So now what we're going to do is we're going to actually structure some motion based on the timer. So the timer will return values in seconds with a precision to about 3 or 4 decimal places to be accurate. So what we can do is we can say if timer.get is less than 2, install what? I have no idea what button I pushed. That was not the intended action. Please do not ask me what just happened. Anyways, so while the timer is reporting a value of less than 2 seconds, we want to perform some action. In this case, we want to drive forward, like I described. We want to drive forward, let's say at half power for 2 seconds. So what I'm going to do is I'm going to say dt.set left-right motor outputs, and then I'm going to say 0.5 and 0.5. Okay? So that's the first part. Now, if we just left it like this, the robot would drive forward for 2 seconds, and then it would stop, because it wasn't being told to do anything else. The default action of your robot for any motors, if it's not being told to do something specific, is stop. So we need to add some other pieces. In this case, we're going to have 4 pieces. So I'm going to say else if, which allows me to define another condition, another reason for doing something some way. And I'm going to say timer.get, whoops, I'm still thinking in the other language and it's bothering me, is greater than or equal to 2. And I'm going to explain why I just put 2 ampersands there in a second. Get is less than 3. Okay. Was that like a half hand raise? It was like a hand cupping, but to your face. Like you were going to ask the question and then immediately decided as soon as I looked at you to not. Sorry, Hunter.
I think I remember what that means.
Ampersands, 2 ampersands in a Boolean expression, a true and false expression, is a way of saying logical and. There are several different logical operators, and, or, and not are the most common ones. And means both sides of the equation must be true in order for the whole thing to evaluate to true. Otherwise, it's going to evaluate to false. Is that one okay with everybody? Or is one or the other or both. So if one or the other of the sides is true or both sides are true, then the whole equation is true. If both sides are false, then the equation is false. And then not is just the reversing operator. If you not true, then it's false. If it's not false, then it's true. Make sense? Mm-hmm. So in this situation, I said else if the timer value is greater than or equal to 2 seconds, and the timer value is less than 3 seconds, then we're going to do something else. That make sense? Okay. So what I'm going to do is I'm going to set left, right, motor outputs. And I said that I was going to pivot, and I said I was going to pivot right. So pivoting right would mean that you would set the left side forward at half and set the right side negative at half. Okay, so that's how you pivot to the right. This side moves forward, this side moves backwards. And then I said in the next second of time, I was going to pivot to the left. Hunter will be able to tell you that I can't always type and talk at the same time. And that's basically it. This will make our robot run in autonomous for 4 seconds. For the first 2 seconds, it drives forward at half power. At the end of that 2 seconds, for the next second of time, it will pivot to the right. At the end of that second of time, for the next second of time, it will pivot back to face forward, more or less, depending on battery power. And then if all of those conditions are false, if that amount of time has passed, then it's just going to stop the motors.
And that's basically just an autonomous or a natural match.
Right, essentially. We had a derivation of that for our robot.
Drive forward.
Essentially. We did have a little bit of turning in there initially, and then someone changed it while I wasn't at a competition. And I think Mr. Klein made the unilateral decision to make it just drive forward and stop trying to put a gear on a peg.
Yeah.
But that being said, a lot of teams that are just starting out will do stuff like this because at the beginning of your match, your battery is supposed to be anyways fully charged, which means your motors are going to move in the most efficient way possible without dragging because the voltage is dropping. So usually for simple stuff, you can get away with using timers. If you're trying to be like dead on one spot, don't bother, but timers aren't going to be an effective way of doing that. Unless you have a very low gear drivetrain that moves at like 3 to 6 feet a second, timers are not going to be a reliable way of positioning your robot during autonomous. That being said, do we have any questions about this piece? Is there anything, TJ?
How would you incorporate like delta time into something like a timer?
Like the change in a period of time? There is a provision for that. If you were looking for the amount of time that has passed in a period, how do I want to demonstrate this? So let's say for a dummy example, because I don't have a better one. Let's say that you, for one reason or the other, wanted to output to the console, it's called the real log, the amount of time that it was taking for your robot to execute teleop periodic. Okay? There is a method called getFPGA timestamp. So one thing that TJ had mentioned to me on the break was talking about other types of variables. And in this case, I'm going to use something called a double. It is essentially a decimal number with an extremely excessive precision. I'm talking like well more than 15 decimal points of precision. I think in Java it's something like 17. In other languages it can be more. But in Java, if I remember correctly, it's 17. And what I'm going to do is I'm going to call this start stamp. And I'm going to set it equal to timer.getFPGA timestamp. And what that's going to do is it's going to ask the FPGA for the time that it knows. There's a special circuit on the FPGA that they designed that is specifically for keeping time. That it is its only job, it does nothing else, and you can ask it for its time at your leisure, accounting for the delay between when Java actually instructs the FPGA to get the value and when the FPGA gets it back to the program. So TJ wanted to know how to do a delta time, a change in time. Now that I've saved the starting time, I can just say the instruction to send to the console, which is system.out.println. I can just say timer.getFPGA timestamp minus start stamp. And that will print roughly, within probably a couple of milliseconds of accuracy, how long it took the teleop periodic method to actually run. there's no good provision for it in the actual timer object when you create one, like we just did. You have to do things like timer.get is greater than or equal to certain time and less than another time sort of deal. But you can use get FPGA timestamp for a bit more fine-grained control. I didn't like using timers when I first started robot programming. All I used was timer.getFPGA timestamp. But whatever weirdness that was in timer originally when I first started using it has since been fixed. So I tend to use that more now than I do the FPGA timestamp method, because it is a very fine-grained timestamp. It has a lot of resolution to it, and it is not as clean as what comes out of timer, because timer does a little bit of cleanup of the timing and makes educated guesses as to the amount of time that it took to receive the information from wherever it asked for it from. So, let's see what time it is. 7:46. I can answer questions. I can do something quick. I don't have time to really start anything else that is extravagant.
And I'm not sure if this concerns like learning schedule, the hands-on build day you keep on talking about.
That I mentioned in the group chat for us.
Okay.
It is on the 16th at Rabicon, the machine shop up the hill.
That's not this Saturday, is it?
No.
Sorry. Okay.
It is not this coming Saturday, but the Saturday after.
Okay.
Part of the reason being is I'm not available this Saturday. I have schoolwork to finish, a final project to finish, and a Christmas party to attend. But by the 16th of December, my schooling will be done. What?
You're gonna be out of school, so what are you gonna do?
Oh no, I'm just done for the semester. I still got a year left. No, next semester is virtualization, database design, computers and culture, project management. I need a
That's
break.
the project side. I have a general question on motor controllers.
Sure.
So they touched on it a little bit with what we've seen so far, but do they have like acceleration curves? You know what that is for
Yes.
motors? Like I imagine like some motor controllers, they have like what's called a soft start, something that just prevents a human from going, oh, 100% boom, you know, because the binary logic would let it do it.
Yes.
Presuming that there's something internal that you can control. So, but I imagine there's some times where you want to accelerate quickly, but how do you prevent them from like, oh, I need to move my arm, wow, you know, have it snap up 100%?
So lately, the trend for FRC controllers has been linear acceleration curves. It's purely linear to the input of whatever the signal is. So if you slam on it,
yeah.
it's gonna go as soon as the motors respond.
Can you rewrite it so that it is like an algorithm that is softer?
You could write a software algorithm that makes it softer. As far as I'm aware, for the motor controllers that are available now, there is no provision to do that in hardware.
But it's not built into the motor controller itself per se.
No,
So if you give it 100%, it's going to try to do it as quickly as it can.
yes, it is not, because of the type of motor controller. It's called an H-bridge motor controller. Basically, the process is the signal that's coming in causes the connection to the motor to switch on and off at a particular frequency.
Yep.
If you slam the joystick forward, it's just going to open that connection and leave it open. But the response time of the motor is then what you're dealing with. and we get back into this conversation that I had during break where stall current comes into play, and the robot slowly starts to build down that resistance as it begins to accelerate.
Yeah, and I guess what got me thinking about it is what we saw when we went to the training in Searsport was that they put in like a parameter, said like give it so much power, like whether 0.2, 0.5.
Yes.
And my question, I guess it's, could you replace that with a formula that says if on positive, take this, curve?
You can, and I have seen teams normally write their own sort of pseudo function that will produce a value for them, that will help to alleviate the sort of whiplash,
falls over, right?
whiplash sort of reaction to motion.
Because I've seen a couple of competitions where you can see some robots like, and others are like nice and smooth as they move around.
And
I
there,
can't imagine that's all skill.
right. And there are some H-bridge controllers that are available to us that have exponential curves. The Victor 888, which is an older controller, no, Victor 884, excuse me. The Victor 884, which is an older controller, which is still legal for use for this year, does have an exponential curve. The problem is a lot of teams don't care to use it because, at least, let me take that back. They don't care to use it on drivetrains because they find it is not natural for what they are accustomed to in video games, is the best way to describe it. If you're playing a driving game, let's say, and you squeeze right trigger to accelerate and you squeeze it all the way down, you expect that sort of slam forward action. Even I sort of expect it when I'm controlling a robot. And a lot of teams are accustomed to that sort of jerky motion. But there are ways to do a softened curve. And it's not usually too bad. A lot of teams will use just like a standard power, like square root and a value, just to make it.
Didn't we do that with Justin? Because he was doing the jackrabbit starts and we were trying to get him to slow down.
I multiplied the joystick values that were coming from the joystick by 0.75 to cap him at 75% power, because our three sims, when they were moving, were throwing the robot back to the point where, even though our robot was squat and heavy, was lifting up off the ground. We were able to pop wheelies with our robot from last year when it was in its basic drivetrain configuration.
And the problem was?
The problem was when it came back down and started flexing shafts like this.
Hard to start flying off.
Right. So there are provisions to do that. You can write from simple to complex functions, depending on how you want to set it up, that can take in a joystick input and choke out whatever your function does. I have seen teams whip out TI-84s and 89s at competitions and do graphs and then write the function into their program and use it for some form of curve. It's usually not on their drivetrain. It's usually on like a shooter or something, but it does happen. Anything else? Posings of any other questions?
Nothing.
I was gonna say anything.
Come on, man.
Any
A question or two.
anything even beyond the programming part of it, even if you want. I mean, it doesn't matter to me.
Anything you want to know?
What's the funniest thing that's ever happened to you at a robots competition?
What is the funniest thing? Oh
There's gotta
my.
be an embarrassing moment where it's like, oh, whoops, I didn't mean to hit that ref.
Okay. Okay.
When you met Justin.
Back in 2011, I was a driver for this team for 2648, and That year was Logomotion. We were putting tubes that were shaped like the pieces of the first logo up on pegs on a wall. And at the end of the match, there's almost always at the end of a match some sort of like mini game component that you have to complete. And that year it was actually backing up to a pole, launching a mini bot that would try to race to the top of the pole quickest, and whoever's mini bot got to the top of the pole quickest got the most points. So I was driving, and my who was, I believe it was Zach or Kristen. I was driving with either Zach or Kristen, and one of them had dropped the guard that allowed us to back up to the pole. And I wasn't able to hear anything. I have an anxiety disorder, so whenever I would get up to drive, I'd have like a little mini panic attack, and my ability to hear would start to go away. And so I didn't hear the buzzer for the end game time, which indicated that I could go put the mini bot up. So about 15 seconds before the match ends, I hear our coach from behind me screaming in my ear. I mean, he must have been two inches behind me, saying, "Go to the pole!" I'm like, initial knee-jerk reaction was to swing the robot around from where it was and back up full steam into the pole. Our guard was aluminum. So when we got out of the match, it was just two pieces of aluminum stuck out like a Y. And the way I had hit the pole, because it had a base on it that you could line up with, the way I had hit the pole, the robot actually rode up on the base and flexed one of the arms like up in, facing the rest of the robot. Luckily enough, the actual drawer slides, like what you have on your kitchen cabinets, were still able to shoot out beyond by where it had stuck up and almost gotten in the way. And we actually were able to get the mini bot up the pole, and I think we were still first in that match. But that was probably the most embarrassing thing, the funniest and the most embarrassing. I when I talk about competitions, I usually like to talk about, you know, different teams that I've seen. You know, I love seeing a team that really has a shooter honed in. There was one team, I think it was either 125 or 1114 in my last year as a senior when it was the game shooting frisbees. They could sit on the opposite side of a 54-foot field and shoot frisbees with like 99% accuracy in their goal on the other side of the field. Just someone standing at their loading station, loading frisbees into the robot, and you just see the thing go, foom, 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 every single one, over and over and over again. I mean, you guys can go on YouTube and look up matches, or the Blue Alliance even, which is a site that stores team statistics and competition statistics and competition videos. You can watch some of these really seasoned veteran teams, and they'll make a shooter that just foom, 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 right from the opposite side of the field where their loading station is, and hit 99% of the time.
Robonauts last year's competition. I only got to see the video, but the shooter apparently could shoot across from the whole field.
Yeah, I mean, like this year with the wiffle balls that had to be shot into the boilers there. There were actually a couple of teams that could literally back up to one of the loading stations of wiffle balls and just sit there and and just cross the field about 45 feet away, every single one right in, like a slam dunk, just nothing but net sort of deal.
Like, have you seen 125 this year with the shooter? Like, I'm pretty sure they got 40 kPa on autonomous.
Oh, that doesn't surprise me. There were a few teams that could do that too.
Messos.
Meso did it a couple of times, I think, or at least they got close.
Too bad the robot broke.
But we've got a minute left. I'm gonna stop this.